back to the GATE Academy. So we are continuing with our series of new addition to GATE 2021 syllabus. And in this series, we are right now covering the portion of steam and gas turbine. So I, Umashankar Tripathi, would like to welcome you back once again on the GATE Academy. I would like to welcome you back on the GATE Academy English channel. So if you have not subscribed the GATE Academy channel till now, please do it so that you will be able to see the new notification and whatever new videos we are going to get live on the YouTube channel. Okay. So here, firstly, let me briefly describe about myself. So who am I? So as you can see on the screen, we are continuing with the topic is steam turbine and gas turbine, which is added in GATE 2021 syllabus. All right, GATE 2021 syllabus we have added. We have a new edition of steam turbine and gas turbine. And my name is Umashankar Tripathi. I am a PhD scholar at IIT Roorkee, PhD scholar that you usually call it as research scholar. Hi, Aniket. So before getting into this PhD program, I have completed my MTech from IIT Roorkee itself. Okay. So as far as the GATE is concerned, so I have this much mark, 65.66 marks in GATE 2014, and with all India rank of 916, on the basis of what I have taken admission in the MTech program of IIT Roorkee. Good morning, Gaurav. Good afternoon. Hi. So in GATE 2015 also I have given and I got 77.02 marks with all India rank of 643. So I am into this GATE teaching from last 8+ years with the GATE Academy. As you know, the GATE Academy has more than 50 centers across India. So before this lockdown, we were used to have the offline classes, but right now we are going for this live sessions and all. Okay, so I would like to request firstly to please subscribe the GATE Academy channel if you have not done it till now, so that you can have the new notification of the live classes we are going to have. Okay, so in this series, this is our 8th lecture or 8th session, you may say. So we are going to continue with this part. Now we have completed all this. This is all is completed. Okay, so you can find these sessions on the GATE Academy English channel. Okay, here also we have completed the compressible flow within this, because this, as you can see, the flow through channel, flow through nozzle. Okay, and here also the impulse turbine part 1. So in these 3 parts, you will find this also. As a responsible student, I hope all of you are aware that this topic is also added in GATE 2021 syllabus. Okay, so if you see all these lectures, it will help in your preparation. Okay, you will be covering steam turbine, gas turbine, as well as compressible flow. So almost all the parts which have been added, all the topics that have been added in GATE 2021 syllabus are thoroughly covered here. So if anyone have not seen the previous sessions and directly seeing this session, I would strongly recommend you go and see the previous sessions also. Otherwise, you won't be able to understand each and every concept nicely. Okay. So now we are going to continue with our reaction turbine part 2. All right. So in the last session, we left at the point where we were going to start with the Parsons reaction turbine case. So before this, what we have established, we have seen impulse turbine, impulse steam turbine, if I may say. So impulse steam turbine we have covered in all the respects. Okay, impulse steam turbine, as discussed, was the combination of nozzle and moving blade. So we have completed this. Firstly, we have completed this nozzle part, and then we have completed this moving blade part, and then we have completed this moving blade part. All right. All right. In the previous session, we have begun with our reaction turbine, and we have established that in reaction turbine, the work done on the blade, in reaction turbine, the work done on the blade is due to, some portion of it is due to the impulsive action of the high velocity fluid stream, as we were discussing, it here, we were discussing it here. So in reaction turbine, what was happening, that in our fixed blade, the velocity is increasing, and pressure is decreasing. So at the entry to the moving blade, in reaction turbine, the steam is having both kinetic energy and pressure energy. So this impulse, what we call here, this impulse is created by the amount of kinetic energy. The kinetic energy the steam is having before entering to the moving blade part, and this reaction is taking place. Due to the pressure energy of the steam we are having at the entry of the moving blade. So we have concluded in the last session that in reaction turbine, work done is produced by both impulsive action and reaction part, that is due to the pressure energy part, due to the changes in pressure energy. Okay. So from there we have said that we can have said, let's say we have some work, and can we say that X% of the work is done by impulsive action or impulse part of the energy, and the Y% is done by the reaction part of the energy. So on the basis of that, we call it 50% reaction turbine or Parson turbine, or 100% reaction turbine or Hero's turbine. Okay. So our working kind of turbine is 50% reaction turbine in most of the cases, or Parson reaction turbine. So we mostly use Parson reaction turbine, or we may call it 50% reaction turbine, or we may call it 50% reaction turbine, or we may call it 50% reaction turbine. This 50% is due to what? Due to the percentage, or the division between how much impulse is there in the work done, how much portion of impulse is there in the total work done, or how much portion of this reaction part is there in the net work done. Okay, so on the basis of that, we are calling the Parsons reaction turbine as a 50% reaction turbine, or vice versa. 50% reaction turbine is named by the Parsons reaction turbine. So this Parson is the name of the scientist who proposed this. So this is the most used kind of the turbine. This is the most of the time we use this kind of turbine in our analysis. Okay, why is it so? Just listen to me. So in a general reaction turbine, let's say in a general reaction turbine, not Parson, not anything, in a simple reaction turbine, what we can see that our work done is as we have seen, V1 square plus V2 square, V1 square minus V2 square, by 2 plus VR2 square minus VR1 square by 2. Now please do not confuse with fluid machinery. This part is almost common in fluid machinery, but there if you go on reading the reaction turbine, you will find another term in terms of the absolute velocity of the blade. So that is there in radial turbine. But as we have established in the previous lecture also, that here it is reaction turbine or any steam turbine, either impulse or reaction, we have axial flow in here. We have axial flow in here. So while when we have axial flow, so our initial velocity and the final velocity of the blade, absolute final velocity of the blade are the same. Absolute final velocity of the blade are the same. So in a general reaction turbine, our work done is given by this relation V1 square minus V2 square by 2 plus VR2 square minus VR1 square by 2. All right. So this is as established. This is first part is our impulse part. This is impulse part. This is the part of impulse, and this is the part of reaction. This is the part of reaction. Now tell me, in any general turbine, what is the input? What is the, let's say, input? So in impulse turbine, the input was, if I talk about unit mass, if I talk about input or inlet energy, you may say, no, Madhusmita, that is not Parson turbine, because in Kaplan turbine, the reaction is not 50%. Okay? Okay? So input we can also call as inlet energy. Input, Francis is not an axial flow turbine, right? So input is equal to the inlet energy. Input is equal to the inlet energy. Okay. So inlet energy is what? Inlet energy is what? So in impulse turbine, what we were seeing that in impulse turbine, we were seeing V1 square by 2, half m dot V1 square by 2. So if I talk in unit mass or for unit mass flow rate, the inlet energy in impulse turbine was V1 square by 2. But here we have some form of pressure energy also, So this represent, as I told, it can also be derived, but I am not deriving it, because reaction turbine we also see in fluid machinery, which is already there in GATE syllabus. So I am not getting into the derivation thing. In impulse turbine discussion, in the discussion of impulse turbine, we almost have derived everything. So I am here by using this relation directly. Okay. So this part, there can be a proof. There is a term called degree of reaction. You may usually see it in fluid machinery if you go for studying the reaction turbine. From there you can comment. That this is the part of pressure energy. So what conclusively, what the thing I am trying to tell, that inlet energy, this is the part of kinetic energy, and this represents the pressure energy. This is kinetic energy, and this represents the pressure energy. Okay. If you have any doubt in it, or you want me to prove it, this lot of time will go in deriving the degree of reaction. And I hope, as it was there in the previous syllabus also, and we are trying to cover most thing newly only. I already have shown you the velocity triangle and everything, which was there also in fluid machinery, but I have showed you here also. But degree of reaction we are not going to prove here. Okay, so from there you can comment. From their derivation, you can comment that this part V1 square by 2 is the kinetic energy, which is creating the impulsive action. And this is the part of pressure energy. Which is actually giving us the reaction. Part, which helps in the motion in providing the motion to the moving blade. All right. So now, if I may ask you, sir, what will be the efficiency of any reaction turbine? Just forget about Parson and anything. Any reaction turbine, if we talk about, no matter how much percentage is the reaction part and how much percentage is the impulsive part, what will be the efficiency? So in general, efficiency is what? Output upon input. Yes or no? So we have also established this fact that in a moving blade, we have this much power per unit mass flow rate is generated. Yes or no? This much power we get to generate. This much power is generated. Yes or no? Can we say that? So yes, this much power we have already have seen all this. So what will be the input here? What will be the input here? So it will be V1 square by 2 plus VR2 square minus VR1 square by 2. So live students can respond to me if they are able to understand it or not, if they are able to understand it or not. So this is the formula of efficiency. You can say this is the formula of efficiency of a reaction turbine. This is the formula of efficiency of the reaction turbine. This is the formula of efficiency we have of the reaction turbine. Okay. So we have to stop a second and okay, just a moment. Huh? There is some technical issue. Sometimes some technical issues happen. Okay, now we are all right. So now our efficiency can be this much. So if you have to find the efficiency, if you have to find the efficiency, if you have to find the efficiency of the reaction turbine, if you have to find the efficiency of a reaction turbine, so we are talking about firstly a general reaction turbine. So don't get confused. I'm rubbing it from it. Okay, we will write it again. We'll write it again. So we are talking about a reaction turbine. A reaction turbine, not Parson, any reaction turbine. This is valid for any reaction turbine. If Parson, it is valid for Parson too. If anyone else, any other reaction turbine, it is valid for that too. Okay. So our efficiency for any reaction turbine can be determined like this, can be determined like this. So you will see that, sir, you will say, sir, this runner power or this is the power generated in a row of a moving blade or in a stage is very much similar to what we have seen in the impulse turbine case. Very much, or I must say that exactly equal to that. But the value of VW1, VW2 will be different. So we can't say that both are giving the same output. Okay. So if I may make the velocity triangle of it, so I think all of you are very much aware of the velocity triangle we are making in the last class also. We are making in the last class also. Yes or no? We have made this kind of these kind of velocity triangles in the previous class. Yes or no? I am showing you the previous classes. Okay, right? We are showing you the previous classes, right? So this is the velocity triangle. This is the velocity triangle we had for the impulse turbine. So let me just copy it so as we can save some time here. And again, I am saying if you have not seen the previous video, you will not be able to understand this class. Okay. So if you have not watched the previous videos, please go and watch it. Please go and watch it. So this is the velocity triangle we were using. This is the velocity triangle which we were using in case of impulse turbines. So let me use it here also for reaction turbine. So in case of reaction turbine, what things you are required to remember, what things you are required to take care is that VR2 is greater than VR1. There we have seen, there we have seen that, there we have seen that, there we have seen that, there we have seen the what, there we have seen what, we have seen that in the impulse turbine that VR1 and VR2 is equal only the friction. If the surface of the blade is not smooth, we will add some blade coefficient. But here VR2 and VR1 are required to be different. So this is the major difference. Rest, the same velocity triangle can be used. Same velocity triangle can be used in reaction turbine. We can make all those calculations and we can make all those calculations as we were doing in the impulse turbine case. So do we need to solve or do we need to analyze this again? Do we need to analyze this again? So I don't feel any need of it. So here we can see there is another method of developing the velocity triangle. So let's just do it by this way. And in this class, we will use that another way of velocity triangle if required. Okay. So the velocity triangle of reaction turbine and impulse steam turbine are gonna be same only. So U1 is equal to U2. So I have drawn this U here. See, so by very much shortcut we can do. If we can memorize a little bit, we can do by very shortcut methods. So see, at the end of u, I have explained this also in the previous lecture. At the end of u, VR1 is starting, and VR1 is starting at the angle of theta. VR1 is starting at the angle of, let's say, theta. We can see the velocity triangle and we can draw it. So this is theta. This is theta. Now I have explained this in the previous lecture as well. So how we can easily or quickly make the velocity diagram using this method? See, remember these few points. At the end of absolute velocity, at the end of absolute velocity of the blade, we can start our relative velocity. We can start our relative velocity. So this is the relative velocity of, this is the relative velocity of what? This is the relative velocity at the inlet. So if I make the relative velocity, if I make the relative velocity for the exit part, it will be equal to VR2. It will be equal to VR2, and the angle between VR2 and U can be seen from here, and that is phi. That is phi. So very easily, very quickly you can make it. Very easily, very quickly you can make it. Okay. Just remember that at the arrow, at the vector, this arrow, from this arrow of u, you have to make the relative velocity. Okay. And from this figure, the relative velocity at the inlet is at theta angle. So you can directly take that theta, and at this velocity, the relative velocity at the exit will be at phi angle. You can take it directly from here. Okay. Now remember, at the beginning of u, from the beginning of u, you have to draw the absolute velocity component. So draw absolute velocity component from this, absolute velocity component from this. So this is v1, this is v1, and with u, it is making an angle of alpha. It is making an angle of alpha, and as I said, at the beginning of vector of absolute velocity of at the beginning of vector of absolute velocity of blade, we must start the absolute velocity of the steam. So you start the absolute velocity of the steam at the exit, and this is what? This is our V2, which is making the angle of beta. This is what? This is our V2. We are making V2 from the beginning of U. Okay. So at the beginning of U, you may draw the absolute velocity components, and at the end of U, you may draw the absolute velocity components at inlet and exit. So this is VF1 and VF2. This is VF1 and VF2. So the rest of the part you can take component. If you take the component of V1, if you take your component of V1, you will get VW1. If you take component of V1 in X direction, you will have VW1. If you take component of V1 in the direction of Y, that is flow direction, so you will have your VF1. Okay. Similarly, you can have your VW2. You can have your VW2 like this. You can have your VW2 like this. So this kind of figure is also very much clear to you. So in this class, we will be using this one. Okay. Is that okay? It will be made in the less time. It will be in less time. Okay. It will be in less time. It will happen in less time. It will save some of your time, and making it is very easy. Okay. You have got the point or not? Is it clear or not? Those who are in live, those who are present in the live lecture may comment and tell me. Tell me. In the comment section. Okay. So as you are telling me, it is clear. Okay. So this is what we have spoken about. It is about a general reaction turbine. Okay. Now, if I may talk about the Parson turbine, 50% reaction turbine. Parson's turbine or 50% reaction turbine, I may choose to call it whatever I want. Parsons turbine or 50% reaction turbine. 50% reaction turbine. Okay, Parsons turbine or 50% reaction turbine. So how will you make the velocity diagram of Parsons turbine or 50% reaction turbine? So you will make as you can make for any reaction turbine. You will make as you can make for any reaction turbine. So the same is the velocity triangle. The same is the velocity triangle of Parsons reaction turbine, in which the effect of reaction is 50% and effect of impulse is 50%. Effect of impulse is 50%. Okay. So what is special about Parsons reaction turbine? So that it is very highly used. It is very highly used. So I am skipping some derivation part. I am skipping here some derivation part. Why I am skipping here? Because for GATE examination, as you know, it is mostly a numerical kind of paper, and we have already discussed a lot, already derived everything a lot. So if you want, you may do it by yourself also. Okay, but that is not required according to me. Rest choice is yours. So here in reaction turbine, what is so special about it? What is so special about it? So if any general reaction turbine, this is happening. Okay, for any general turbine, VR2 is greater than VR1. VR2 is greater than VR1. So here it is also VR2 will be greater than VR1. But what will be the special about it? So in a Parsons reaction turbine, this you can use directly. So alpha is equal to phi. Alpha and phi are equal in Parsons reaction turbine. You can even develop it. You can see it by taking 50% impulsive effect, 50% reaction effect. This result will come. This result will come. But according to it, that is not required. Because in GATE examination, finally you are not going to derive it. Okay, although we are going to derive the maximum efficiency of it, we will have the derivation of maximum efficiency of it. But this derivation is not required. That how sir alpha is equal to phi. So you can directly memorize it. What else? What else? So if you are going to see it, so V1 will be equal to VR2. VR will be equal to VR2. Beta will be equal to theta. Beta will be equal to theta. Beta will be equal to theta, and V2 will be equal to VR1. V2 will be equal to VR1. So this you can use exclusively. This you can use exclusively for Parsons turbine. Only for Parsons turbine. Please remember, not for any turbine, not for all the turbines. Only Parsons turbine. Only Parsons turbine. For only Parsons turbine, you can use this condition. I am never saying that for any reaction turbine you are go and use this relation. Only for Parsons turbine you can use this relation. Okay. So what is so special about Parsons turbine that it is getting so much of use? Because as I told you in the previous lecture too, that Hero's turbine, which is 100% reaction turbine, which is first developed steam reaction turbine, or first developed working steam turbine. So axial thrust there was very much, but in Parsons turbine, this can be asked in some theory objective. So axial thrust is neutralized. All this can be seen mathematically too, but to making thing easy, I am giving you the observations so that you can have it and you can use it if the question is being asked. So our axial thrust is neutralized. Blade design becomes simpler. This we will prove how blade design will become simpler. Blade design will be simpler compared to the other kind of reaction turbines. So simpler means easy to manufacture also. You can play with English. Easy to manufacture also. Easy to manufacture. And thirdly, the efficiency is good, or efficiency is better than the other reaction kind of turbine. So we can say efficiency is near optimum. So these are one can say these are the features of the Parsons turbine and why it is so popular and why it is being used in most of the places where reaction turbine is used. Okay, so Parsons turbine is a very famous turbine used in many applications. Okay, so these are the reason behind it. So let us now derive the expression for maximum efficiency. Let us now derive the expression for maximum. Yes, today, sir, axial thrust is neutralized means VF1 is equal to VF2. It's not like that actually. VF1 and VF2 are there, but their magnitude is very, very less, you can say. Or see, when you put, see, these, as I said, randomly saying anything won't be right. If as I said that you can derive all this, 50% impulse part you put, 50% reaction part you will put, you will see why the axial thrust is getting neutralized. Okay, so randomly without derivation, let me not say anything about it. Okay, okay. So these points, see, is I am giving you these all these points. I am giving you all these points. Now, if I try to give you a derivation of this also and this also. This session will go in that only. In that only. So see, this new syllabus is added in GATE examination. So steam turbine, gas turbine, and compressible flow. Steam turbine, gas turbine, and compressible flow. So this is our, how many sections we have completed? We have already completed 7 sessions, and this is our 8th session. 8th session. Okay. So already we are giving so much to this new topic, so much to this new topic. Okay. So we should not make it like a subject. It is a part of a subject. But if we go on studying this and deriving this and that, so it itself will be created like a subject. So whatever unnecessary derivation we are having, we may avoid it. We may avoid it. Although till now in all the sessions I have derived almost everything what I have said. I have proved everything all I said almost. Okay. So you please follow that, and in the same pattern as we have derived everything in the impulse turbine and the nozzle thing, in the same pattern you can derive it here, and you can see. You can see. Okay. But now our intention is to take this steam turbine and gas turbine. Gas turbine we have not started yet. So we are trying to now take this steam turbine towards its conclusion. Okay, towards its conclusion. Okay, so that we have this clear distinction. So any one of you must be thinking, sir, in 16 hours you have 16 hours have gone and you are still teaching steam turbine. So I would say no. In that 16 hours, 8 hours I have taught compressible flow also. Okay, 8 hours of compressible flow also is included. Okay, so you are covering parts in 2 topics, as I said. Also, we have covered impulse turbine, which is common in fluid machinery. Yes or no? So that also you are getting to cover here. We have also used Bernoulli equation. We have used some part of fluid mechanics here. We have seen some part of thermodynamics here. So all along, if you see, if you see, so many subjects are the participants here. Whatever we are learning here, you can apply it directly to the Kaplan turbine also, no problem. Okay, Kaplan turbine also. So you are getting to learn at a time in many subjects. If you learn them individually, that we people do mostly, that we want to we today we think of is studying compressible flow. We will open some fluid mechanics book, read it in some other way. Then we will open some power plant book, and their compressible flow through the nozzle will be given in some other way. Then we will study that. Then we will make us remove. We will try to memorize both things separately. So what we have tried to did in this session, we have converged all this knowledge. And as I have shown to you that we are doing everything. Till now, I have not used any new relation. I have just naming them. Compounding was new. That is also a new thing. But Bernoulli equation, whole compressible flow we have seen with Bernoulli equation. Okay, continuity equation, and the relation of adiabatic process of thermodynamics. Mostly these 3 equations were used, and we have developed every other relations every other relation in compressible flow using these three relations. In a steam turbine, in the analysis of moving blade, we are using the knowledge we have from the fluid machinery part. Okay, okay. So if you see this in that way, if you see this in that way, you will say that 16 hours or 18 hours or 20 hours are sufficient here. Okay. So next we are going to use the gas turbines in the further lectures. Okay. So now let us derive the maximum efficiency for Parson turbine. Maximum efficiency for Parson turbine. So in case of Parson turbine, just take a look here. In case of Parson turbine, you must remember this. In case of Parson turbine, you must remember this. All right. In case of Parson turbine, you must remember all this. That alpha is pi, beta is equal to theta, VR1, V1 is equal to VR2, and V2 is equal to VR1. So what is the maximum efficiency of Parson turbine? So what is the efficiency of any turbine? What is the efficiency of any turbine? So for any reaction turbine, the efficiency is VW1 plus VW2 into U upon V1 square plus VR2 square minus VR1 square, and I am multiplying 2 above. Okay. Similar discussion we have done in the impulse turbine case also. Almost similar discussion we have done in the case of impulse turbine also. Okay. So this is the efficiency of any reaction turbine. So what is my target here? What is my target here? As we have done in impulse turbine case, we want to reduce everything in terms of initial velocities, and blade velocity. So in order to do that, let us use some relation we see from this velocity triangle. So I think this triangle, you people, Harsh, I already checked the denominator. I have sent that 2 to the numerator. Okay. Instead of writing this 2 in the denominator here, I have sent it in the numerator. Is that a problem? I don't think there is a problem. Okay, so we are very much now aware of using this velocity triangle. So let us use it. So quickly we will do VW1 is equal to V1 square, V1 cos alpha. Are we doing it for the first time or we are doing it many times? Let me paste it here so that you can see how I am writing this. So VW1 is equal to V1 cos alpha. VW1 is equal to V1 cos alpha. Harsha, is that okay or not? So we have VW1 is equal to V1 cos alpha. Okay, from this we can say something like that. Okay. VW2, what VW2 we are having? VW2 we are having as we already using this relation VR2 cos phi minus U. You can see from here also. From this, see, this is VR2. So this much is VR2 cos phi. This much is VR2. From this point to this point, it is VR2 cos phi. And if I subtract U from it, it will be VR2 cos phi minus U. So see here, VR2 and V1 are equal. So can I write VW2 is equal to V1 cos phi minus U, and also the phi is equal to alpha. So we are doing it for Parson turbine. So we can say that this is alpha. So this replacement is understood to you or not? VW2 is nothing but V1 cos alpha minus U. VW2 is V1 cos alpha minus U. Okay, so these VW1, VW2 have been reduced into the inlet terms, into the terms of inlet parameters. Okay, now what is left? VR2 and VR1. Now see, VR2, VR1 are the same only. So VR2 is equal to nothing but V1. Okay, so this is also replaced. This is also replaced. So now we have to replace this VR1. We have to replace this VR1. Now see, I'm copying this figure again now. I'm copying this figure again now. Okay, so let us see here. This is unnecessary. Okay. Okay. So now let us see this. Let us see this. So from here we require to find VR1 now. In our equation, only VR2 is not in terms of the initial parameters. So let's just try and convert VR1. VR2 is converted into initial parameter. VR1 is to be converted. So now can we say now VR1 is equal to, let's see, VF1 square. Let's say VR1 square is equal to VF1 square from this triangle. If you can focus on the triangle. So VR1, this is VR1 from the green pen. This is VR1 from the green pen. So by using Pythagoras theorem, I am writing is VF1 square plus VW1 minus U square. So if you make figure like this, it is very handy to take the values. Otherwise, you have to see somewhere in the inlet triangle, outlet triangle. So whatever you find easy, you may choose. Whatever you may find easy, you may choose. So we have VR1 square is equal to VF1 square plus VW1 minus U square plus VW1 minus U square by using Pythagoras theorem. All right, by using Pythagoras theorem. Okay. Now we also know. Now we also can say that V1 square is equal to VF1 square plus VW1 square. Can be or can't be? V1 square is equal to VF1 square plus VW1 square. We can see from this bigger triangle in which V1, VF1 and VW1 are there. Getting my point or not? Getting my point or not? Tell me. Tell me. Tell me. Getting my point or not? Now see. We have to make a little iterations here. We want to replace something. We want to have some replacing. So can we say VF1 square plus VW1? Can I write like this? VW1 minus U plus U. Is there any problem? Is there a problem if I write like this? If there are problem, if I write like this, VW1 I have written like VW1 minus U, VW1 minus U plus U, VW1 minus U, VW1 minus U plus U. Okay. So here we can expand this. Here we can expand this. Here we can have this expanded and we can write V1 square is equal to VF1 square plus VW1 minus U whole of square. Just expanding. I am using the formula of A plus B square. So tell me if you feel any issue, you can let me know. If you feel any issue, you can let me know. Okay. Plus 2U VW1 minus U. 2U VW1 minus U. Yes or no? So this thing, see this thing, this part can now directly be replaced by VR1. You can do it other ways also, whichever way you find easy. The ultimate target is to convert VR1 in terms of V1 and V1 and velocity of the blade at inlet, or absolute velocity of the blade, whatever we may want, we may say. So V1 square will become VR1 square. We can write like this: VR1 square plus U square minus, we can say 2U W1. We can say 2U W1 minus 2U square. I have opened this bracket now. So now we can say that V1 square is equal to VR1 square minus U square. This is VW1. Okay, this is VW1. So minus U square minus 2u VW1. So from here we can say that VR1 square is equal to V1 square plus, if I made some mistake, if I have made, just let me know. Just let me know. Okay, I have used this as minus. This is plus only. No, this is plus. This is plus. Okay, so please follow the, please follow whatever, please follow the derivation. I have used plus here, so I have made this correction. So V1 square plus U square minus 2U, and VW1 we know V1 cos alpha. V1 cos alpha, yes or no? Yes or no? So from here we have this value of VR1. From this relation we have this value of VR1 in terms of, we have this value of VR1 in terms of initial terms. Say yes or no. Those who are live can respond to me. Say yes or no. So now we have VW1. Let's highlight it. So we have this VW1. See, I am trying to convert everything. Into inlet parameters. So VW1 we have, now VW2. This is VW2 in terms of initial parameters. V1 already is there in initial parameter. This is VR2. And now this is VR1. So now replace all these highlighted values. All these highlighted values in the equation of efficiency. If we replace all this highlighted value in the equation of efficiency, what we are going to get? So this efficiency will come out to be, I'm just placing the value of VW1, VW2, VR1, V1, everything. So it will come out to be VW1 plus VW2. It will be 2V1 cos alpha minus U, VW1 plus VW2, VW1 plus VW2. Okay. 2V1 cos alpha minus U. See here, if we add VW1 plus VW2, V1 cos alpha will become twice and U will remain single. So it will be 2V1 cos alpha minus U upon we had a V1 square. Plus VR2 square. So VR2 is nothing but V1 square. Okay. And that is VR1 square. So VR is minus VR1 square, VR1 square. So if I put the value of VR1 in the efficiency equation, it will be like this: minus V1 square minus U square minus 2U V1 cos alpha minus 2U V1 cos alpha. So the relation of efficiency will be like this, where this V1 square can be cancelled out. So the efficiency will become now 2V1 cos alpha minus U upon V1 square minus, or this will be plus, no, this will be plus because minus VR1 square there, na? So it will be plus. So V1 square plus, let's say 2U, and there is a U outside also, na? There is a U outside also. So let me multiply this U inside. I'm just placing the value. Don't get confused. See, U is outside there now also. So I was left with this U. So I'm just placing the values. Do not worry about it. It's a very simple thing. So if I multiply U inside, the equation will be like 2V1U cos alpha minus U square. 2V1U cos alpha minus U square. And in the denominator, it will become like 2UV1 cos alpha minus U square. So here we have the formula of efficiency. In terms of basic parameters. So somewhat this kind of thing we have done in the study of impulse turbine, that you can see in our previous sessions also. So from here, what we require U in the condition of maximum. So as we are aware, and I already have told you, whenever this term comes, condition of maximum, we somewhat go to differentiate the parameters with respect to some other parameter, and put it equal to 0. So we may choose to differentiate this with U, but as you can see, the relation is very big. So let us reduce this relation. Let us now reduce this relation to some easier terms, so that we do not make mistake. We do not make mistake while differentiating. So let me use this speed ratio. A speed ratio, is a constant term. A speed ratio, is a constant term. So we have this speed ratio is equal to Cu, and it is U1 upon V1. It is U1 upon V1. Okay. So let me replace U in efficiency equation. Let us call it equation number 1. So in equation, good afternoon. So this equation, in this equation number 1, we are required to replace this U. We are required to replace the value of this U. So let us replace this U in there, in that equation. So it will become 2 and 2V1. So U is V1 Cu. Cu is what? Our speed ratio. Okay, speed ratio. Why I am doing this? Just to make this equation a little bit easier for our differentiation part. So U square will become V1 square Cu square. U square will become V1 square Cu square. U square will become V1 square Cu square. Okay. And in the bottom, what will happen? The relation will become like this. V1 square will be there, plus 2 V1U. So I am replacing this U now. So this U I can replace with Cu. So we can write V1 Cu, and it will become cos alpha, and then there is minus U square. So we can write like V1 Cu whole of the square. Okay, just doing some mathematics, nothing else. Okay, so from above and below, you see that we have somewhat like this left: 2 Cu cos alpha, minus Cu square. Okay, upon we have it, V1 square is cancelled out. See, there will be a V1 square term everywhere in the numerator and everywhere in the denominator. So V1 square will be cancelled out, and it will be like 1 plus 2 Cu cos alpha minus Cu square. So this would be the denominator. So this can be asked directly. This kind of relation can be asked directly can be asked as the relation of efficiency with respect to the speed ratio. Efficiency with respect to the speed ratio. So tell me now, if I do something like this, that I add a plus 1 here, let me take this 2 as a common. We can write like this. So if I do a plus 1 and minus 1, will there be a problem? So this efficiency can now be written as 2 times. So this plus 1, if I take, this will become 1, and it will be 1 minus 1 plus 2 Cu cos alpha minus Cu square. 2 Cu cos alpha minus Cu square. So this efficiency will become like this. This is also a relation that can be asked. Okay, this is also a relation that can be asked. Okay, this is also a relation that can be asked. So So now if we move ahead, now we have this relation. Now can we can we differentiate it with respect to Cu and put it equal to 0? If we differentiate it with respect to Cu, if we put it with respect to Cu, if we differentiate it with respect to Cu and put it equal to 0, we will have our speed ratio for the condition of maximum efficiency. So let's just do it. Let's just do it. So this 2 and 1 is a constant. It will be cancelled out. Minus won't do any difference because we are putting it to 0. So it will be minus 2. It will be 2 cos alpha minus 2 times Cu, that is equal to 0. If I differentiate this, this will come. If I differentiate this, this will come. Yes or no? So from this we can say our optimum speed ratio is Cu. The speed ratio should be equal to cos alpha. For what? For maximum efficiency. For maximum efficiency of Parson turbine. This is what for we are doing it for Parson turbine. So for maximum efficiency of what? For maximum efficiency of Parson turbine. For maximum efficiency of Parson turbine. Got it or not? Got it or not? So if you want to find the U, we can say that U is equal to V1 cos alpha. So if our blade velocity equal to V1 cos alpha, we will get the maximum efficiency. Now, can we put this back into equation number 1? Can we put it back into equation number 1? We will have our maximum efficiency if we put it back into equation number 1. Okay. So if I put this U back into equation number 1, I hope all of you can do some simple mathematics. So if you put this for maximum efficiency, if you put back U or Cu, whatever you want, in your maximum efficiency formula, you will get this. So we have seen something like this in impulse turbine also. And there also we have concluded that the design of, this is the formula of maximum efficiency. So the design of the impulse turbine, the design of the blade of impulse turbine is simple because the design depends upon only one angle, and that is alpha. So here also the maximum efficiency, of Parson turbine is in front of you on the screen, and you can say from here that this maximum efficiency depend upon the alpha. This maximum efficiency depend upon only one angle, and that angle is alpha. All right. Okay. So from here we can say the design is simple because it depends upon only one angle. So when the design is simple, we can say it is easy to manufacture. Okay. And we have seen this efficiency as a function of alpha. So by managing the alpha, we can optimize the efficiency as well. So all this formula I am deriving, it is important for objective. Can be directly asked in objective examination, or since this topic is recently added, we can have a question like this also, that the value of alpha is this, Now tell me the maximum efficiency of a Parson turbine or 50% reaction turbine. So are we clear till this point? Say yes or no. Are we clear till this point? Say yes or no. Are we clear till this point? Okay, thank you, Anand. So now let us solve a question and we'll go and conclude with the reaction turbine. Okay. Let us now copy this question from here. Just give me a moment. I have already typed the questions for you. Okay. So here we go. So let me increase the font size of it. I think this much is better. Or we shall increase it even further. Okay, now it is fine. Now it is fine. So I can say all of you can see it, or should I increase it even further? Okay, now I have increased it a lot. Now those who are in the live session, can now start solving this question, and we can have your answers, and then we can proceed. Those who are seeing this recorded as a recorded video, you please also solve this question so that any doubt will be solved in that time. I'll be solving at the time. I'll be solving this question. Okay. Okay. Now please continue and solve this question. Now please continue and solve this question. So I would again like to request you all to subscribe the GATE Academy channel. Okay. So we are almost concluding our steam turbine. In the next session, we are going to see governing and critical speed part. But as of this session, we are going to see one more thing after this question, that is reheat factor. And then we are going to summarize all what we have learned till now. And then we'll call it a session. We'll call it a day. So our next live session will be on Monday. Okay. By that time, all the live students are requested to go through all the sessions again, make your notes, have your doubts ready, have your questions ready. We will have them cleared on Monday and Tuesday, because we have 4 sessions left with us. In that, we'll be covering the gas turbine part. We'll see what we can in the gas turbine part. Okay. Now please solve this question. Sorry. So can we consider it a Parson turbine? So we cannot. It is not mentioned anywhere. It is not mentioned anywhere. So consider it as a simple any reaction turbine. Consider it as any reaction turbine. And here we have to calculate degree of reaction also. What is degree of reaction in general? What is degree of reaction in general? So degree of reaction is the ratio of the pressure energy to the total energy. All right. So if degree of reaction, if you have problem in that, let me just write it here. So degree of reaction is what? Degree of reaction is what? The total change of, you can define it like total change of pressure energy, total change of pressure energy in a moving blade or in runner, whatever you want to say, upon the total change upon the total change of energy in the moving blade. Okay, so whatever change has happened in the pressure energy to the overall change is known as the degree of reaction. So what is the change in pressure energy we have seen? VR2 square minus VR1 square, VR2 square minus VR1 square by 2. This is the total change of pressure energy. This is the part of the pressure energy we have seen. And what is the total energy? Sorry. So what is the total change of energy? What is the total change of energy? The total change of energy is VW1 plus VW2 into U. Okay, I am writing in terms of unit mass. Okay, so this is your degree of reaction. Okay, so we already know the total change of energy happens is equal to the power of the blade. Upon what is the part of this power played by the pressure energy. So can we have the answers please now? Those who are live can give me answers. I will wait here for a while. And we'll wait and we'll see your answers. Let's say this is the last question what we are doing in Steam Turbine. Last numerical, we have seen some numericals previous sessions also. Okay, so this is the last numerical we are going to see in Steam Turbine. So certainly you require more practice, so you can follow any book for numericals if you want to. If you want a recommendation of the book, P.K. Nag is a very good book. Dr. P.K. Nag have written that book. So that book is a very good book of power plant. Okay, you can go. There are many examples there. You can solve them. You will have the idea. All right. Yes, Anand. Phi and alpha both are 20 degrees. So let us start with this question. Let us start solving this question. So we have a speed of steam at the exit of the fixed blade is 150 meter per second. Now let us take some time here. This is the last question, so we will give some time here. So a speed of the steam at the exit of the fixed blade is 150 meter per second. So any one of you who is live can tell me what is this? Can anyone tell me what is this 150? What is given? What is given to you? 150 is what? This 150 is what? Can anyone tell me what is this 150? Anyone? What is given? What is given this 150? What is this 150 given to you? What is this 150? So it is, as you are saying, it is V1. Now see. In reaction turbine, as we have established, there is no nozzle but a fixed blade which acts somewhat like a nozzle. Okay, which acts somewhat like a nozzle. All right. So, a speed of steam at the exit of fixed blade is 150. So this is nothing but the absolute velocity of steam at the inlet of moving blade. So it is V1. And the flow ratio. Flow ratio is what? So we have seen the flow ratio. Yes or no? What is the flow ratio? So flow ratio is VF upon, flow ratio is what? Flow ratio is VF upon U. Yes or no? We have seen it while we were discussing the impulse turbine, that flow ratio is defined as VF upon U. Okay, so what is given? It is given that the flow ratio at the inlet is this and outlet is this. So this means that the ratio of VF1 by U1 is given as 0.75, and VF2 by U2 is given to be 0.78. So this is also given to us. This is also what is given to us. All right, this is also what is given to us. Now, if mass flow rate is 2.8 kg per second, so what else is given to us? M dot is given to us, and it is 2.8 kg per second. It is 2.8 kg per second. This is m dot given to us. Okay. What else is given to us? So the discharge blade angle of both rotor and stator is 20 degrees. The discharge blade angle of both rotor and stator is 20 degrees. So discharge means what? Exit. So exit angle of the rotor is given to be 20 degree. And what is this exit angle of the stator? So we have developed in the last session, the exit angle, the exit angle, the exit angle of the fixed blade is nothing but the entry angle to the moving blade. When we were seeing the staging or curtive, when we were solving the velocity of two-row curtive, the problems of two-row Curtis velocity turbine in the previous section, we have established this fact that the exit angle of the fixed blade is nothing but the entry angle to the moving blade, or we can say the fixed blade angle or nozzle angle, whatever we may want to call it. Okay. So see, last but not the least, let us give you some suggestions. So the suggestion is always try to get the or always try to identify the data right, because if you are not able to identify the data, if you want to identify the data, if you won't identify the data correctly, your question will be wrong. So Harsh, you are asking how to find it as Parson turbine. Sir, it is not a Parson turbine. It is not a Parson turbine. All right. It is not a Parson turbine. If it is Parson turbine, it would have been given to you. If you, it would have been given to you, or you can cross check with this condition. While moving ahead, you can cross check with this condition. Do not, if not given as a Parson turbine, do not take it as a Parson turbine. Do not take it as a Parson turbine. But if all these conditions are getting satisfied, then you can call it a Parson turbine. The conditions are on your screen. That alpha should be equal to phi, alpha should be equal to phi, beta should be equal to theta, V1 is equal to VR2, V2 is equal to VR1. When all these conditions are satisfied, the turbine will be Parson. If not, the turbine is not Parson. So why to get confused in it? You consider it as a general reaction turbine. If it is a Parson turbine, then also the answer is going to get correct. Or if not, then also the answer is going to get corrected. Okay. So you consider it as a general turbine, general reaction turbine, and solve it. All right. All right. So now we have this velocity triangle. Okay. We have this velocity triangle. So let me copy it again. Where is our velocity triangle? This is our velocity triangle. Okay. So this is our velocity diagram. I have taken alpha is equal to 20 because it is given in the question. See, in the last lecture, what we have established, if you have attended that the exit angle of the stator. Now see, focus on this selected statement. The exit angle of the stator is 20 degrees. So it means what? It means what? The exit angle of the fixed blade only, no? So we have established this, that the exit angle of the fixed blade. We have established this, the exit angle of the fixed blade. The exit angle of the fixed blade is the entry angle to the next moving blade. This is what we have seen in when we were seeing the carryover coefficient in the previous section. Okay. So now we are having this diagram, and what we require inlet rotor blade angle. So we require theta. So for theta, we require what we require? All these values. Yes or no? For theta, we require all the velocities values. So let's just go and find these values. So can we find VW1? Can we find VW1? Tell me. Can we find this VW1? So yes, we can find VW1 is V1 cos alpha. All right, VW1 is V1 cos alpha. So if someone of you may call me, give me the answers, give me the values, it will be very, very helpful of yours. So V1 is given to be 150, so it is 150. Cos alpha is given to us at cos 20. So can someone tell me the value of VW1? 328. Sir, how you got 328? I think it would be equal to 328 because 150 into cos 20 if you do. VW1 is what? V1 cos alpha, na? We have seen this in many problems previously also, in previous sessions also we have seen this. In previous sessions also we have seen this. So VW1 is V1. Can somebody calculate it and tell me? Anyone? Yes, sure. Theta is right. So let me calculate it for you. So it is coming out to be 140.95 as told by Aishwarya. So it is 140.95 meter per second. So all of you can calculate with me. So it is 140.95 meters per second. So we have this VW1. Why we have calculated VW1? Because we require to get the power also. We require to find the power also. So it will be used in future. So we already have calculated it. Now VF1 will be what? VF1 will be what? VF1 will be V1 sin alpha. So can somebody tell me the value of VF1 also? VF1 sin alpha. Can someone give me the value of VF1 also? So this is 150 into sin 20. This is 150 into sin 20. So can you tell me the answer of it? What is VF1? So it is coming out to be 51.3. Thank you. So VF1 is 51.3. All right. All right. So if we have VF1 from this flow ratio, can we have U1? And once U1 is found, no, flow ratio is different, so we cannot comment if U1 and U2 is same or not. That we'll see. So if we can find the U1 from here, what will be the value of U1? What will be the value of U1? What will be the value of U1? Anyone? 51, we are putting the value of VF1 here. So it is coming out to be 68.4. And that will also be equal to U2 because we are having the axial flow turbine. So VF1, VF2 will not be equal, but U1, U2 will be equal. Okay, because this ratio, flow ratio is different. So U1 is U2 is equal to equal. So can you tell me the value of VF2 now? So VF2 is equal to 0.78 into U2. Yes or no? Tell me the value of VF2. Tell me the value of VF2 now. What is VF2? What is VF2? What is VF2? So it is coming out to be 53.35. So we are calculating all the velocities value first, because in this question we have to find the work done as well and the degree of reaction as well. So we are ultimately going to have that required. So now if we have VF2 from this triangle, can we have the VR2? Can we have the VR2? So yes, we can. We know sin phi is equal to VF2 by VR2. Sin phi is equal to VF2 by VR2. We know this. So from here we have the value of phi, we have the value of VF2. Can we have the value of VR2 now? We have this one, we have this one. Okay, so we can have the value of VR2 now. Can anybody tell me the value of VR2? So it is coming out to be someone 156 meter per second. 156 meter per second. Okay, 156 meter per second. Okay, So now we have, as we have the VR2 value, we can have the VW2 value. We can have the VW2 value, and VW2 is nothing but VR2 cos phi minus u. All these things, all these formulas we are taking from the velocity triangle. You draw it in front of you, you will be able to get it. Just resolving the components of velocity. So we have this VW2 now. We have this VW2 now from here. So we can put the value of VR2, we can put the value of cos phi, we have the value of u, so we can have the value of VW2, and that is coming out to be 78.2 meter per second. So we have the value of now VW2, we have the value of now VR1. VR1, let's see if anything is left. If anything is left, so we didn't calculated the value of VR1. We didn't calculated the value of VR1. So let us calculate the value of VR1 as well. Let us calculate the value of VR1 as well. Can we calculate? Can we calculate the value of VR1 now? Can we calculate the value of VR1? So VR1 will be calculated. Let's first calculate the theta. Then it will be easily be calculated. Okay. So we have to find the inlet rotor blade angle. So let's first find the inlet rotor blade angle. So we have this. We can write like tan theta. Now see, we are doing the same thing again and again. So this is VF1 upon VW1 minus U1. VW1 minus U1. So from this relation, you have VF1, you have VW1, you have U1. Okay, let's see what is VF1. VF1 is 51.3. Let's see what is U1. U1 we have calculated is 68.4. And VW1 we have calculated as 140.95. So if you place the values here, what will be the value of theta? Can somebody tell me what will be the value of theta? What will be the value of theta? Anyone? What is the value of theta? What is the value of theta? Anyone can tell me? $35.26. So if you calculate from here, your theta will come out to be 35.26. Your theta will come out to be 35.26. Your theta will be 35.26. Is that clear? Is that clear? So we have calculated the first part of this question. Now let us go for the second part. So we require the power. So let us first calculate VR1 here. So VR1 will be equal to, how will we calculate? So VR1 will be equal to, let's say we can do that Pythagoras theorem also, or we can do like this also. Already we have the value of VF1. So we can put the value of VF1. Now we have calculated the theta value. So we can put it here, and we can have our answer. So can somebody will tell me the value of VR1 too also? Can someone tell me the value of VR1? What is VR1 coming out to be? Shall I calculate myself? Or any of you will telling me? Going to tell me? Just tell me. So should I calculate myself? Anyone? Okay. Thank you, Yash. So you are giving me the answer as 88.8. 88.8. Okay, very nice. I am relying on the calculation you guys are making. Okay. So we have this value of VR1 also. So let's highlight it. This is going to be used. Now the second part is we have to calculate the power. So power is m dot VW1 plus VW2 into U. This is what m dot is, VW1 plus VW2 into U. So we have this value of m dot. we have this value of VW1, we have this value of VW2. Can we find, we have this value of U also. Can we find the value of power? We have everything with us. We are having everything with us. Mass flow rate is also given 2.8. So can somebody will tell me the answer? So this is 2.8. This is 2.8. VW1 we can place. Where is VW1? We have calculated it. We have highlighted it. So it is 140.95. So just placing the values. And VW2 is 78.2 and U is we have calculated as 68.4. So from here, as you are suggesting me, the answer is 41.96 kilowatt. Okay, I don't know if it is correct. If you have made the calculations correct, it must have been correct. Now C part, what is the degree of reaction? We have to calculate at last the degree of reaction. We have to calculate at last the degree of reaction. So the degree of reaction we have seen is what? This is the formula of degree of reaction. This is the formula of degree of reaction. So we have the value of VR2. Let's check. Let's check. So we have the value of VR2 or not. So yes, we have the value of VR2. Now check, we have the value of VR1 or not. So yes, we have calculated this VR1 too. Now we have this value of VW1. Yes, we have this value of VW2. Yes, we have this value of U. Yes, so we'll have your degree of reaction from this formula. Is that clear or not? Is this question clear or not? Tell me. Tell me, is this question clear or not? Tell me this much is clear or not? So we have this value of degree of reaction. Can someone tell me the value of it? Can someone also tell me the value of it? Can someone please tell me the value of it? Degree of reaction, what is coming out to be? So our reaction turbine is also completed. Our reaction turbine is somewhat also completed. And now you can solve the questions by yourself. You must have got the idea how to study, what to study. Okay. And if I think if you watch all the lectures, all the sessions of this series, everything will be clear to you. Everything will be clear to you. Your efforts will be minimized. All right. So now we are moving to the last topic for this session, that is reheat factor. That is reheat factor. Okay, very simple. Very simple. So reheat factor, how it is defined, let us write the definition of it. So reheat factor is the combined, let us like this, combined, or let me directly write the formula of it. So let's say there is two stages. Let's say there are two stages in a turbine. So reheat factor is the isentropic, is the combination of isentropic enthalpy drops of all the stages, or we can say combined isentropic, combined. Actually, we are leaving the last question, just let it go. Now I hope when the value, when you have all the values, okay, when you have all the values, you will put it in the equation and you will find the answer. Okay, so we are continuing with the next topic, that is reheat factor. So now what is reheat factor? So reheat factor is the ratio of, so this delta H1s plus delta H2s means what, and so on and so on. If they are more than two stages, if they are more than two stages, so on. So reheat factor is the ratio of, we can say, is the ratio of, is the ratio of combined or cumulative. It is the ratio of combined or cumulative isentropic enthalpy drop, combined or cumulative isentropic enthalpy drop for each individual stage to the total isentropic to the total isentropic to the total isentropic to the total isentropic enthalpy drop from initial to final stage, from initial to final stage. Okay, so this is how we define the reheat factor. So if we have, let's say, two stages, so there will be a isentropic enthalpy drop in the first stage. There will be some isenthalpic entropy drop in second stage. Okay, so if you sum them up and divide it with total isentropic enthalpy drop, you will get your reheat factor. Now, obvious doubt arises, sir, this all must be same. No, this should be same. No, the reheat factor must be equal to 1. No, so it can be 1, it can be greater than 1, it can be 1, it can also be greater than 1. Now let's see what reheat factor actually means, or what it is actually is. So let's say we have an enthalpy entropy diagram. Now let's see. Let's listen to it. Listen to me carefully. You will get. Listen to me carefully. You will get. So let's say we have these two pressure lines. And this is our initial stage, and this is our final stage. Let's say let us call this by 3. So we have if isentropic enthalpy drop is taking place in, let's say we have only one stage. So this much, try to understand the concept. So this is our total enthalpy drop. This is our total enthalpy drop, isentropic. S sign represent isentropic. So isentropically enthalpy is dropped from 1 to 3. So this distance is our HTS. Okay, this distance is our total isentropic enthalpy drop. But if we are now doing it in stages, so if one is my initial stage, so if I expand isentropically, let's say I have 2s point, and if I expand it to 3, we call it 3s. So S denote that we are expanding isentropically. Okay. So can you say, now see very carefully. Now can you say that this is our delta H1s? Okay. This is the enthalpy drop in the first stage, and this is the isentropic enthalpy drop. This is the isentropic enthalpy drop. Can we say, sir, this is the delta H, in second stage, and as it is isentropically expanding, we can say that, sir, there is no problem. This is our isentropic enthalpy drop. So what will be the reheat factor here? So it will be 1. Why it will be 1? Because delta H1s plus delta H2S upon delta H TS. So this will be 1 because they are same. This will be 1 because they are same only. If you sum up delta H1S and if you sum up delta H2S, they are same only. So why introducing the heat factor? Because they sometimes can be different also. How they can be different, or try to understand it from here. Try to understand it from here. Now we have our HS diagram. We have, let's say, three pressure lines. Three pressure lines. So this is our inlet, this is our inlet, this is our inlet. So if from inlet the expansion took place isentropically till point 2, we do not mind. We have this 2s. We have this 2s. But what can happen? What can happen? We have seen that actual it may be, this is actual, let's say it is 2a. So actually it is expanding like this. So actually not by 2a, I represent it by 2. So this will be our delta H1a. Delta H1a means actual enthalpy drop. So if the expansion is not isentropic, so this is our actual enthalpy drop in the first stage. Yes or no? In the first stage. But you will say, sir, delta H1S will not change. So yes, it will remain same. It will remain same as of the above case. It will remain same as of the above case. But my dear friend, this will change now. So previously, what was happening? That from 2s it was going to 3s. So our delta H1S plus delta H1 H2S was equal to that delta HT. But now we are going to this 3 point. Let's say isentropically. So previously this 3 point was here. So your total enthalpy drop was till this much. Total enthalpy drop will be till this much. Okay, but now this is your, and this is a straight line. No, remember this, na? How we are calculating it? We are putting it like this. Okay, we are seeing it from here. So if you draw a line, a straight line from here, if you draw a straight line from here and a straight line from here, so this will be your delta H1S. This will be your delta H1A. Okay, and this will be your delta H1S. This, see, I am making it by blue line. I am extending this. So this was your delta H1S. Okay, this was your delta H1S. Okay, so here we go now. In the next stage, if the expansion take place isentropically, so we will have this delta H2S, So here reheat factor will not be coming to be 1, it will be greater than 1. Got my point? Because reheat factor is what? It is equal to delta H1S plus delta H2S. So now here delta H1S and delta H2S will not be equal to delta HTS, as you can see from this diagram. Clear or not? Tell me, is this clear or not? Those who are live can respond. To me. Is this clear or not? Is this clear or not? You have to compare both of these figures. Okay, so as we are responding to me, is this is clear to you? So now, no, now if I take stage efficiency into consideration, if I take stage efficiency, if I take stage efficiency into consideration, so let us call a stage efficiency like this. So stage efficiency, we have seen that actual enthalpy drop upon isentropic enthalpy drop. See, this is very simple. Actual enthalpy drop to the isentropic enthalpy drop, we can see. Okay, so if two stages are there, this is the stage efficiency of the first stage, and stage of efficiency of the second stage will be delta h 2a upon delta h2s delta h2s. So this is your stage efficiency of the second stage. This is your stage efficiency of the second stage. So if you may write it like delta h1a is equal to stage efficiency of stage 1 plus this, and if we may write delta h2a is equal to stage efficiency of stage 2 into delta h2s. So will there be a problem? Will there be a problem? So if we consider stage efficiency equal, so let's say all the stages have same stage efficiency. So if we add these equations, what we are going to get? We are going to get delta h1a plus delta h2a into 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 this, or in the bracket we will have delta h1s plus delta h2s. So I have done nothing. I have just added these two equations. I have just added these two equations. Okay. Isn't it clear? This is, let's say, equation 1. This is, let's say, equation 2. So if I add equation number 1 and 2, what will happen? We may write like this: delta h1a plus delta h2a is equal to, so we have considered the stage efficiency as equal. So this is stage efficiency. So this will be delta h1s plus delta h2s plus delta h2s. Is that right or not? Is that right or not? Is that right or not? So can we divide this equation by, can we go on and divide this equation by delta h ts, and this also by delta h ts? Will it make any difference? Will it make any difference? So no, it is not going to make any difference. It is not going to make any difference. So this is what? This is what? This is overall efficiency. Okay, this is overall efficiency, because the numerator is showing us what? The actual enthalpy drop, in the turbine, and in the bottom is the total isentropic enthalpy drop. So this is nothing but the overall efficiency. So overall efficiency will be equal to the stage efficiency and the reheat factor. So we have this relation which can be used in objective type of questions or in certain examples. So in this equation, we have related the overall efficiency with the stage efficiency and reheat factor. And as we have established that reheat factor is greater than equal to 1, so can we say that if reheat factor is greater than 1, our overall efficiency is greater than the stage efficiency or equal to the stage efficiency? Okay, got my point or not? Got my point or not? Tell me, got my point or not? So is this reheat factor clear to all of you? Is this reheat factor clear to all of you or not? Yes or no? Yes or no? Yes or no? Is this clear? Yes or no? Live students can respond to me now because this steam turbine part is almost completed. In the next lecture, we are going to see the critical speed or the governing, how we can govern the steam turbine. Okay. Some theory part is there. We will see in the next lecture. But numerical part till now is clear. So how this can be used in numericals? So how this can be used in numericals? So if I give you the stage efficiency as, let's say, 80%, 80%, will you be able to solve? Will you be able to calculate and reheat factor, let's say 1.05? 1.05, will you be able to calculate the overall efficiency? Anand, in this formula, we have considered all stage efficiency as same. So you can consider if nothing is otherwise mentioned. If nothing is otherwise mentioned. Okay. Okay. Otherwise, you follow this rule. You have to go step by step. Otherwise, you have to go step by step. All right. So if we have the stage efficiency, can we have the overall efficiency? Can we have the overall efficiency? So you will say, sir, yes, sir. If a stage efficiency is 80% and its reheat factor is 1.05, we can have our overall efficiency is equal to 0.84, 0.84. So this overall efficiency can be related with the actual enthalpy drop to the theoretical enthalpy drop, Say yes or no. 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 Tell me. Okay. So from here, if I give you, see how questions can be framed. So from here, if I can give you that, sir, what is the theoretical? If I give you, let's say that theoretical isentropic enthalpy drop is given to you. Let's say this is given to you. We call it as TS, no? So we call it as TS. So let's say it is given to you. It is given to you, let's say 1000 kilojoule per kg. I'm taking some data. I just trying to tell you how questions can be framed from here. So it is going to be 1000 kilojoule per kg. So you can calculate, if it is given, you can calculate the actual total enthalpy drop. Yes or no? So it will be somewhat 840 kilojoule per kg. 840 kilojoule per kg. Okay. So if I tell you that the number of stages is 15, let's say. 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 So what will be the actual enthalpy drop? What will be the actual enthalpy drop in each stage? Will you be able to find me that? Will you be able to find me that? So you can divide this 840 from 15 and you will have the actual enthalpy drop in each stage. This actual enthalpy drop in each stage. Tell me yes or no. Is that clear or not? Is that clear or not? Is that clear or not? So this actual enthalpy drop is what is giving you, this actual enthalpy drop is giving you this power at the rotor, yes or no? So you can equate it with this. And here again, you have come to this velocity triangle thing. So some data you will be able to find from here, and then other data you will be able to find from the velocity triangle, what we have seen, cos alpha this, cos phi this and that. So by till this equation, this thing will guide you. This reheat factor, this stage efficiency may guide you, and from here onwards, you can apply the basic fundamentals what we have seen of velocity triangle and can proceed in the question. So how questions can be framed from this? You also have got the idea. Yes or no? Yes or no? Yes or no? So now this numerical part of a steam turbine is completed in all respects. Okay. In the next live session on Monday, we are going to see some governing and critical speed of the steam turbine, and then we'll move to the part of the gas turbine. So governing and critical speed is what you see in your theory of machine part also. Okay, so that is the information we collect from the theory of machine. I will guide you how to apply it if asked, although it is very less tentative. If asked, you can apply those concepts of theory of machine here in the steam turbine. Here in the steam turbine. All right. So let me summarize what we have seen till now. So in the first lecture of this series, we have seen about the introduction, the classification, the specification and all. Okay. First lecture was introduction. First session was of introduction. So from here, you can find some details about how we classify, what is the basic difference of impulse and reaction turbine. What is the classification? Harshal, let me summarize this, then I'm giving you the answer to you. Okay. So summary, first session, we have the introduction in which we have classified the steam turbines in two ways. We have seen how we can do the specification of it. We have seen the basic differences of impulse and reaction turbine. So you will find all these things in the first lecture, the basic introduction of this steam turbine, how what is different from the previous GATE syllabus and what. Okay. In the second session, third session, fourth session, and some part of the fifth session, we have seen flow through the nozzles or about the nozzles. So here you can say we have seen the compressible flow also. We can say the compressible flow also. Okay. So we have analyzed the nozzles. Okay, we have analyzed the nozzles by using our basic equations of continuity, Bernoulli steady flow energy equation. Nothing special we have used. Some formulas we have developed. So please go and watch those sessions too. After then, we have started with the impulse turbine. Okay, we have seen the types of impulse turbine on the basis of blading. Okay, we have seen the level, we have seen Ratiu, we have seen Curtis, means simple, pressure compounded, and velocity compounded. Okay, and we have solved examples of that. We have seen how to make the velocity triangle. We have seen how to derive the maximum velocity, as well as we have solved some questions on the simple turbine as well as the compounded turbine, where we have used the carryover coefficient, and all. After then, we have begun with the reaction turbine. So these last two sessions, this session we have dedicated for reaction turbine, but although it is very much similar to the impulse turbine, so our discussions are very much limited. So lastly, we have covered this reaction turbine. You have seen what are the differences of reaction turbine with impulse turbine, mathematical differences, analytics differences. And now we have solved some questions on reaction turbine and have seen the reheat factor as well. Okay. So according to me, if you read all this, if you understand all these concepts, it is very good. This part can be asked in GATE 2021, and very positive chances are there because it is a very good thing, very numerical based thing, very conceptual thing. So in GATE examination, the question makers are kind of searching for this kind of topics from where they can throw you, or they can give you, they can attack you with some concept, good formulas, good numerical. Okay. So can I have some response? How was this series till now in the comment section? And meanwhile, let me explain to the what is not clear to Harsh. Inlet energy is not clear to Harsh. Okay. So Harsha, I'll try to clarify the inlet energy. Okay. The inlet energy. So inlet energy we can say, see, in reaction turbine, there is no nozzle. So after a fixed blade, the steam pressure has been reduced to some extent, and its velocity is increased to somewhat some extent. But in impulse turbine, what was happening? In impulse turbine, what was happening? The whole pressure drop took place before our steam enters the moving blade region. Steam enters the moving blade region, but in reaction turbine, not the whole pressure drop took place. So steam enters the moving blade part with some kinetic energy, with some pressure energy, and that complete energy is going to help us provide the torque while flowing through the moving blade. Okay, so that is why I'm saying this first part is the kinetic energy part, and the second part is the pressure energy part. Okay, got my point, Harsha? Thank you for the comments. So if you have not subscribed, again I'm requesting, if you have not subscribed the GATE Academy channel, please do it. Please do it as soon as possible. You will get good videos. Okay, you will get good videos here. Okay, so I will see you. We'll continue this series from Monday onwards. So we have 4 lectures left in this series. So we will see some part of theory of machine that we can apply in this steam turbine thing, like governing critical speed, and then we'll move to the gas turbine section. Okay, in the gas turbine section, we are not going to again see this velocity triangles and all. So we will talk about the cycle, we will elaborate the cycle to some extent, and we will see the actual gas turbine cycle also, and we'll see some of the components of the gas turbine cycle also, because the discussion for the gas turbine, the blading and all is the same what we have seen till now, and it is same what you have already seen in compressors also. So we are going to analyze the cycle of the gas turbine. Okay. So thank you very much. Please do subscribe the GATE Academy channel. My name is Umashankar Tripathi. I hope you are enjoying the series. So with this, if there is no doubt, we can end this session. If there is no doubt, we can end this session. So thank you for watching the video. Thank you for watching the video. Here on the screen, you have the contact details of the GATE Academy. For any query, any feedback, any suggestion, for any information regarding the ongoing live classes schedules, you can contact us. You can subscribe our channel so that you will get notification of the live videos. Okay, and whatever new topics we are going to discuss on this channel. Okay, so please do subscribe, please share to your friends also, and please recommend to your friends. Okay, so thank you very much. So I am signing out. If there is any doubt, so I consider it as no doubt. So thank you very much. Thank you for watching the video.